Ahoy, I'm Sava. Let's talk about graphs and control policies. Shortest path on a graph is the problem of finding a path between start and target vertices that minimizes the sum of edge costs. It's a well-studied problem. For example, you can solve it using A* or by formulating a network flow LP. The dual program to the network flow LP has the interpretation of searching for the lower bound on vertex potentials, or cost to goes. It's basically searching for a good admissible A* heuristic. Shortest path on a graph of convex sets, or GCS, replaces nodes with sets. Now when you go through an edge, you must pick left and right points from the corresponding sets. Not surprisingly, dual to GCS also searches for a cost to go, but in space. It's a piecewise affine cost to go with affine chunks associated to sets. Think about it as a spatial admissible heuristic, a good lower bound on the true cost to go. Now in class we saw that cost to goes for control systems immediately give you a control policy. Just pick a control input that greedily takes you down the cost to go gradient. Now dual GCS gives us a cost to go, so in theory we should be able to use GCS as a policy. That's what my project is about. It's a very general framework, but for this video I'll focus on a simple case. We'll search for a piecewise quadratic cost to go. They're expressive but not too computationally heavy. We'll look for a cost to go over a horizon of n steps, and we'll want them to be good admissible heuristics over a region of space, not just one point. Our system will have linear dynamics with quadratic cost, and we'll have obstacles. My first example is a sanity check. A double integrator into D, no obstacles, goal is to get to 0. We know the solution here. It's LQR. Optimal cost to go is quadratic. It's given by the Riccati difference equations. And indeed, GCS as a policy exactly recovers the Riccati equations. I'm plotting trajectory realizations here. Nothing amazing, but a good sanity check. Okay, something more interesting. Big obstacle in the middle, go around the corner. Hey, this is really good. It picks up the turn nicely. Remember, I'm not replanning trajectories from each initial condition. I'm just going down the cost to go gradient. But hey, you might go, not impressed? It's an easy problem. Don't need no fancy cost to goes, just use the one from LQR. Sure, it'll take you into the wall, but you can just solve a small QP at each time step to remain collision-free while going along the gradient as best you can. Easy. You're right, this would work, but you would incur an average 30% more cost than GCS here. And you see, LQR got lucky there. As soon as we have proper complex scenarios, then LQR fails, goes straight into the corner and miserably accrues infinite cost. While the GCS policy makes a beautiful turn, and it takes the faster route too. This is mint. And this math is very general. If you have a polynomial dynamical system, you can use GCS to search for a piecewise polynomial cost to go to get a solid control policy. In theory, this is profoundly general and expressive. In practice, solving semi-definite programs is still hard. Cheers.